Welcome to the fourth workshop. In this workshop, we will focus on altering pixel art using rendering channels. We'll delve into the process of creating a normal map based on pixel-drawn patterns, analyze and overcome challenges encountered during the production. Lastly, in this practice workshop, we'll combine relatively simple texture maps like color, transparency, emission, and roughness into an artifact. This artifact will be transformed into pixel art altered by rendering channels. Throughout this workshop, you will learn how to create more intricate normal maps within the workflow of altering pixel art using rendering channels. First, we'll explore what a normal map is in the field of rendering. To grasp the concept of normal maps, it's essential to have a clear understanding of the term normal. In geometry, a normal refers to a vector or line that is perpendicular to a surface or object. In the field of rendering, a normal map is a specialized type of texture used to simulate fine surface details and textures on 3D objects. It is particularly popular in real-time rendering contexts like video games and computer graphics to enhance the visual realism of 3D models. There is an image shows their appearance. As seen on the left, we have the original appearance of the object, while on the right, we observe the appearance of the object's normal map. A normal map contains information about the direction of the surface normals at each pixel, indicating how the surface is oriented locally. By applying a normal map, rendering engines can simulate how light interacts with the surface, creating the illusion of additional details and depth. This means that even though the geometry of a model remains the same, the normal map makes it appear more complex and realistic. Now, let's delve into the experimental process. I began this experiment following the practice-related research approach, aiming to explore potential knowledge and issues. My task was to create a simple pixelated wand, enhancing its pixel art effect using a normal map. In the first attempt, I tried constructing a 3D version of the wand over the original image as a reference, then baked its normal map. Unfortunately, this initial experiment ended in failure. The method proved challenging to control, making it difficult to create a wand perfectly aligned in size with the background image. Additionally, adjusting the model after building it became cumbersome. An error in the lower part of the baked pattern further compounded the issues. We will explore the reasons behind these problems later in this process. Eventually, I decided to abandon this approach, so my conclusion is to not recommend using this method. In the second attempt, I manually cut out squares on the mesh and adjusted the heights of vertices, edges, and faces. However, this approach presented two significant issues. First, due to manual alignment with the reference image in the background, the final product couldn't perfectly match the pixels in the reference image. This required meticulous inspection of areas with misalignment and readjustment. Second, when I adjusted the model's protruding parts, triangular faces appeared, leading to the creation of triangles. We'll delve into the reasons behind triangular faces and how to address them in the following sections. To address the alignment and height adjustment issues, I embarked on the third practice. To ensure alignment with the background image, I used a method where the number of face cuts was set to the pixel image's resolution -1. For instance, if the pixel image was 32 by 32, I cut the faces 31 times to achieve precise alignment. Following this, I adjusted the height of each face. The final result was that every pixel was accurately matched. This method proved to be highly suitable. Simultaneously, in this third practice, I attempted to remove the background region for model baking, which ultimately led to a problematic normal map, as shown in the figure. The next part is about the problems that we met during the experiment. Problem 1: Triangular faces. In this experiment, I created a face and subdivided it into 9 smaller faces, with the central one marked in red for clarity. As I adjusted the heights of the points, edges, and faces within the red central face, I closely observed the outcomes. Here's what I discovered. The first one, it's crucial to ensure that within a single face, no individual point should have a different height compared to the other 3 points. The second one is, for the 4 points of each face, it's essential to make sure that a single point shares its height with one of its adjacent points. For example, if one point on the red face is elevated compared to the other 3 points, it results in the creation of triangular faces, as depicted in the image. There are 2 methods to address the issue. When ensuring that neighboring points within the same face have at least 1 point at the same height, the red face no longer produces triangular faces. However, an issue arises when the neighboring faces fail to meet this condition. As a result, triangular faces emerge in the adjacent faces. This phenomenon is explained in detail in the following part of the workshop video. To resolve the issue described above, there are two methods. The first method involves isolating the red face from the others and then adjusting its height. The second method entails extruding the red face and then modifying its height. In the ongoing experimentation with the 9-grid setup, where various modifications were applied before baking, here are the outcomes. 3 methods proved successful in achieving error-free bakes. These methods are as follows. 1. Keeping the background faces. 2. Keeping the adjacent background faces. 3. Removing the vertical faces while retaining the background faces. On the contrary, 4 methods led to baking errors during the process. These problematic methods include 1. Removing all background faces. 2. Filling the bottom. 3. Removing both the vertical and background faces. 4. Removing the main body. The normal map will disappear. This thorough experimentation unveiled specific approaches that ensure error-free baking, as well as those to be avoided. Finally, I proceeded with the 4th round of practice. This time, I adopted an approach that ensured the absence of triangular faces and baking errors. I retained the background portion except for the main body of the staff. Afterward, I successfully baked the one-sided model of the staff to obtain an accurate normal map. Additionally, I created metallic roughness, opacity, and emissive maps for it. When combined, they produce the following effect. This exemplifies the concept of 3D altering 2D pixel art. In this workshop, we embarked on a creative journey to explore the world of normal maps and their transformative potential for pixel art within a 3D context. We uncovered challenges and solutions, delved into successful baking techniques, and ultimately witnessed the magic of enhancing pixel art with 3D realism. Remember, in the realm of art, there are no limits to what you can create. Keep experimenting, keep pushing boundaries, and keep turning your imagination into reality. The world of 3D altering 2D pixel art is yours to explore and conquer. Happy creating!